Thank you very much. Thanks you to all of you to be here. Indeed, my title was Ergodic Theory of the Geodesic Flow of Hyperbolic Surfaces, and the goal of the lectures, in view of the subject of the week and the subject of the trimester, it will be to construct a family of measure, a family of invariant measure, a good family of such invariant measures, good in two senses. First, they reflect the chaotic behavior of the geodesic flow, what that means. And second, they are useful and used to study some questions of deformation of geometric structures on hyperbolic surfaces. And probably I will have not enough time to develop the second point, but among geometers, too many people are afraid from these measures, and so I would like to develop the construction and the properties of these measures so that if you want to learn about this, you will not be afraid from these measures. So before to go into the details of this construction, I guess that the audience is more geometric and I want to speak about dynamical systems. I would like to say a few words about what chaos is. What does it mean? The first thing is that, probably it's a word for journalists more than mathematicians. There is no definition of chaos. But there is an intuition about chaotic behavior. So I would like to recall some things. So first, let's return to elementary probability theory. Imagine you are on a square. So your probability space is the square, and your probability measure is just the Lebesgue measure on the square. Okay, that's a nice probability system. And now define an event A, which will be, I don't know, some interval times 0, 1. So A is this event. Okay? And second, let B be another event, which is another interval times 0, 1 times another interval. That's B. Okay? These sets are two events in probability language, and you can check, that's not even an exercise, that the probability of A intersected with B is the probability of A times the probability of B. Okay? That's completely elementary. Why do I focus on it? I would like to insist on the fact that you have a product space, 0, 1 times 0, 1. It's a product space. And you have a product measure. It's the Lebesgue measure times the Lebesgue measure. And then what you see is that when you have events that depend only on the first coordinate and another event that depends only on the second coordinate, then they are independent. In other terms, the coordinates x and y are independent. Okay? So that's very important, because we will see later that the geodesic flow has this kind of product structure which creates some chaotic behavior. The second thing that I would like to recall, another source of chaos, is what happens in expanding dynamics. So you can consider, for example, the angle doubling map. So on a circle, you consider the map that if you have an angle, you at each time you double it. Okay, and then I will stop pictures. And it's easier to write it as follows. If you have x in 0, 1, you associate it to it 2x mod 1. That's the same map. This map is uniformly expanding. You have this factor 2 here. Okay. This means that if you take 2 points, say, I don't know, if you take 2 points on 0, 1, such that maybe distance of between x and y is maybe 2 to the power minus 12, then they are, you cannot distinguish them, but after, say, 11 iterations, then they will arrive at macroscopic distance. Okay? What I'm saying is that if you have a uniformly expanding dynamics and you have 2 extremely close points, after a very short amount of time, they are at a macroscopic distance. That's a way to obtain chaotic behavior. Okay? Of course, why did I speak about that? Because geodesic flow has some properties like that. Okay, so what is a geodesic flow? Maybe I will define it with a picture. You consider the hyperbolic disk, and you consider any vector with norm 1, v, tangent to the hyperbolic disk. A tangent vector defines a unique geodesic to which it's a unit tangent vector at the origin. And, okay, say it's like that. And then the geodesic flow moves vectors along the geodesics that it depends. So GTV is a vector tangent to the same geodesic at distance t. Okay? And what can we say on this flow? Many things. In fact, there is a homeomorphism called the Hopf coordinate that I will come back on it later. I would like just to show it on the picture. If you have your vector v, you can associate to it some coordinates. So first, observe that the dimension, stupid remark, the dimension of d is 2, the dimension of TD is 4, and therefore the dimension of the unit tangent bundle is 3. You have an equation, so you decrease the dimension. And then, okay, so I need 3 coordinates to describe my vector. I have, the first one will be the endpoint at infinity here. The second one will be the endpoint at infinity here. And the third one will be a real parameter that I will define later, which tells you where you are on this geodesic. Okay? But it's not so surprising that you have such an homomorphism. And so what I'm saying is that, okay, you have product coordinates. Okay. If you want to be completely correct, you should notice that you are not allowed to have the same point here. A unit vector has 2 distinct endpoints at the infinity, but I will forget this detail. It's not a problem. It's just to focus on the product structure. So you have a product space, okay? And if you look at this product space, let me emphasize that these coordinates represent the past of the geodesic. These coordinates represent the future, and this one represents the time that moves from past to future, okay? And then you have this product structure, and if I find, in my first example, if I find a good measure, which is a product measure, then I will hope to get this kind of independence properties showing me that the past and the future is independent. So I will write it. It's for the moment, it's just an heuristic, but it's the goal of the lectures. If I can produce a product measure, it will allow to get independence between the past and the future. And if you think a second to it, obtaining independence between the past and the future means that you have a chaotic behavior. It exactly means that the past does not determine the future. That's a way to say that it's chaotic. So that's an important remark. And the second remark is that in this coordinate, one could show, I will not enter into details, but it is the case, one could show that the geodesic flow acts on these coordinates by translation here, contraction here, no, expansion here and contraction here. Or the contrary, that's not important. So here, so I will write it. Okay. There are many things that are not explained when I say that, because I should give you a good distance on the circle for which what I say is true, but still it's true. So it acts by on S1 times S1 times R by translation here on the real coordinate. What did I write? Contraction here and expansion here. And so expansion here, as in the map angle doubling map, expansion will create chaotic behavior. So I do not give details at the moment, but these geometric features of the flow will create chaotic behavior. Okay? And the geodesic flow is most well-studied hyperbolic flow, most well-studied another flow, because of these geometric characteristics, which are extremely explicit and allows to work easier than in general hyperbolic dynamics. Okay, but come back to this picture. In dynamical system, we are interested in understanding the long-time behavior of orbits. Look at this. Take a vector, move, and then you arrive at infinity. It's not extremely interesting. Okay. So this dynamics is stupid. Okay. You take a vector, it moves. Okay. So of course there is a relation between my lectures and the preceding ones. We will consider quotients of the hyperbolic disk, on which the topology will create some recurrence. And so I should never let my notes on the table. Oh, that's not the good. I try to follow my notes. It's difficult for me. Yes, so the general framework will be a hyperbolic surface S, which is a quotient of the hyperbolic disk by a discrete group of isometries. And then the unit tangent bundle of the surface will be the unit tangent bundle of the disk quotiented by the group gamma. And we will study the geodesic flow on such a surface. So typically, when gamma is a co-compact lattice, the surface looks like that. And you take a vector, you look at the geodesic that it defines. Okay. And the orbit will move here. And at infinitesimal level, the product structure that you see here will create expansion and chaotic behavior. But at the global level, orbits stay in a compact set. And so maybe you have interesting things to say. Probably yes, because I'm here. Okay, I draw a picture of a compact surface. And I will focus mainly on compact surface in these lectures. But my preferred situation is when, okay. Huh? No, mais. So here, say gamma will be often a co-compact. And if you are not used to dynamics of the geodesic flow, please think to co-compact lattices. But okay, my preferred area is when gamma is not a lattice. And not even, there is a situation which is for dynamical people. Okay, I will come back to the distinction that Fanny proposed yesterday. You have the co-compact lattices. You have the finite volume lattices. You have the convex co-compact. Groups. And you have the geometrically finite ones. And then you have the rest of the world. Where is the rest of the world? I don't know. Okay. The rest of the world, you could imagine, for example, my favorite one would be, okay, no, I don't know. You could look at infinite covers of compact surfaces, or you can, okay, you can consider many non-compact surfaces, but I decided not to speak about it in this lecture, so I will stop. But if I come back to this distinction that Fanny explained yesterday, you have co-compact lattices, non-compact compact lattices, convex co-compact surfaces, geometrically finite surfaces. And in fact, for the point of view of dynamics, convex co-compact are the same as compact. From the point of view of dynamics, it's really the same thing. But okay, anyway, in these lectures, I will focus mainly on these examples. Yep. Okay. So now I would like to introduce you a little bit to ergodic theory and to what does cow mean from the point of view of ergodic theory. So I should say what is ergodic theory. So you consider a flow on a certain space X, which will soon be the geodesic flow on the unit tangent bundle of a hyperbolic surface. And so we are interested in long-time behavior of orbits. And okay, the behavior, what is a chaotic behavior? As I said, it's a kind of a journalistic word, not a mathematical one, but one could say that the behavior of the dynamics is chaotic when you have many different behaviors. Precisely, you have many orbits that are very different one from the another. That's a way to say that you have chaotic behavior. So that's not a definition, that's an intuition. I'm not. So if I come back to the picture of a hyperbolic surface, I have a hyperbolic surface. I have many distinct trajectories. For example, I have periodic trajectories. Here, I have a periodic trajectory. I have more complicated periodic trajectories that you saw yesterday pictures of I'm completely unable to draw things like that, but you have many complicated periodic orbits. But you also have many dense orbits. You can have dense orbit. But you have many ways to be dense. You can be dense everywhere with the same frequency, but you can be dense, but with a small density here, and most of the time you are here. But still you go regularly here, so you are dense. And okay, so you have many infinite different ways to be dense. In fact, the goal of the lectures is somehow to show you that if you imagine a trajectory on a hyperbolic surface, essentially it will exist. So if your brain is able to produce a trajectory, then there will be a trajectory doing almost the same thing that you wanted. Okay. Another way to describe cow in a dynamical system is to quantify the number of orbits. The concept is entropy. What is entropy? Entropy is a way of counting orbits. So imagine you have how do you say that? Glasses, and glasses are very bad glasses. So they have a precision epsilon, and so you don't distinguish anything closer. Two things that are closer than epsilon, you don't see any. You don't distinguish them, okay? And with your bad glasses, you try to count between time 0 and t how many orbits of length t I can distinguish. So in this way, so you fix epsilon and you count. So you will count kind of tubes of orbits epsilon close. Okay, and how many such different? In French, I would say boudin, but I don't know how to say in English. So you count how many tubes you can see up to epsilon until time t. So here you have 0 and here you have t. If you have many, many different trajectories, then even up to epsilon, you will see many different things. And maybe it will grow so fast that it will grow at exponential speed. Okay? So entropy is the exponential growth rate of this number of different orbits until time t. So entropy is the exponential growth rate of the number of distant orbits, pieces of orbit between 0 and t. Of course, if you are used to it, definitions of entropy are more painful, but the idea is exactly this one. And okay, if you have positive entropy, it exactly means that you have an exponential growth rate of different orbits. So it exactly means that you have many, many different behaviors. That's in the same thing. Okay, and then another way of saying that there is chaotic behavior is mixing. The mixing property, for the moment, I have no measures. So from a topological point of view, mixing means that you start from any set, and then after a while, you will go to any other set. So for every open set, after some time t0, you know that you will always be able to go from U to V. Okay, these are notions that do not involve invariant measures, but now I would like to speak about invariant measures. Ah ouais, il faut faire séparer. Yes. Ah mince, il faut effacer le tableau. No, I'm sorry. Okay, as said Nicolas, for the moment I didn't introduce measures, but okay. So these notions were topological. Topological in the sense of topological dynamics, there is no measure. Now I want an invariant measure. What is an invariant measure? And in these lectures, all my measures will be probability measures. Okay, it's a measure on the unit tangent, on my space X, such that for every t, if I push my measure by my dynamics, okay, I get the same measure. In other terms, if I have a Borel set, the measure of phi minus TA is equal to the measure of A, and then you can also see it with functions. So for all continuous function or measurable function from x to r, the integral of psi you have this relation. That is an invariant measure. Okay, and from the point of view of I'm lost in my notes. From the point of view of ergodic theory, the first notion that we want to introduce is ergodicity. The measure M is said ergodic if you cannot decompose it. What? Oh, yes.
Both the version with the sets and the version with psi are equivalent?
Yes, yes. No, they are equivalent. That's different vocabularies, but that's the same. A measure is said ergodic if you cannot decompose it. What does it mean? It means that if each time you have a decomposition of your space as a set A disjoint union with a complementary set, with an invariant set, then such a decomposition is necessarily trivial. It means that either A is of measure 0 or the complementary set is of measure 0. So that's ergodicity. And ergodicity has a very nice consequence, which is the Birkhoff-Ergodic theorem. Which has almost a century. What says Birkhoff-Ergodic theorem? It tells you that if X is if the measure is ergodic with respect to the dynamical system, then each time you take an integrable function and you consider the ergodic average of psi along an orbit, I learned during my PhD that it's better to say ergodic average instead of Birkhoff average, because there are two ergodic theorems that have been published at the same time, the van der Maan ergodic theorem and the Birkhoff ergodic theorem. And Birkhoff was a very nice editor who hid the van der Maan paper to publish before. So it's better to speak about ergodic average and not Birkhoff average. I try to do it. So, but Birkhoff ergodic theorem says that ergodic averages almost surely converge to the integral of psi with respect to M. Okay, maybe I will emphasize that it's normalized, but if M is a probability measure, this term is is 1, but and this convergence is true almost surely with respect to M, and it's true for t going to plus or minus infinity. Okay. And okay. What it tells you, if you think to psi as the indicator function of a Borel set, it tells you that a typical orbit will visit A asymptotically proportionally to the measure of A. Okay. Another, so in particular, it already tells you that you have different orbits, because No, okay, that's not exactly what I wanted to say, so I removed my sentence. What I wanted to say, the problem is that I cannot read my notes. Sorry. Okay. I would like to emphasize something that has been a problem for me because, okay, maybe I'm doing ergodic theory, but I had a geometric, I began with geometry, and this is true almost everywhere. And then you can ask, if you have many invariant measures, what does mean this theorem? That's a real question. And for a given vector, what can you say of its ergodic average? That's a very complicated question. And in general, you have very few satisfying answers. So that's hidden beside the theorem. Je sais pas du tout. What I wanted to say, okay. I will be interested in a situation where, okay, I will call M1 will be the set of measures on the unit tangent bundle of my hyperbolic surface that are invariant under the geodesic flow. Okay, now I'll come back to my favorite dynamical system. My favorite dynamical system is the geodesic flow on the unit tangent bundle of a hyperbolic surface. Okay? And I look at all the possible invariant measures. And yes. That's the one here. But I didn't say it. Thank you. So I'm interested in invariant probability measure on the unit tangent bundle of my hyperbolic surface that are invariant, and often they will be ergodic. So if I consider ergodic measures, I will add it. Okay? And the point is that, okay, what I wanted to say, in view of Birkhoff ergodic theorem, if you have many invariant measures, then you have many different behaviors. So if M1 is big, then the dynamics is chaotic. That's a way to quantify. So maybe I should. There are many ways to say the behavior is chaotic, and this is one. Okay, and then if I look at the time, maybe I should say, okay, M1, okay. In the good situation, when the surface is compact, this set M1 is a compact convex set. But it has typically infinite dimension. That's for geodesic flow, in fact, it's a huge set. Okay. Other ways to quantify chaotic behavior? Yes?
What about this argument in this convex compact case?
Good question. So what happens in the convex co-compact case? We will see later that from the dynamical point of view, compact and convex co-compact is the same in the sense that in the convex co-compact situation, so here, all the interesting trajectories stay here. That if you cross this periodic orbit once, you will never come back. You go to infinity and you never come back. And from the dynamical point of view, it's not interesting to go to infinity. And so if you have an invariant measure, for example, it's a consequence of Ergodic theorem that an invariant measure, probability measure, is necessarily supported in this part of the space. So in fact, from the point of view of dynamics, the good set, the non-wandering set for the dynamics, the good set for studying invariant measure is compact. It's not exactly the convex core that Fanny introduced yesterday, but it's the set of vectors whose endpoints are in the limit set. And this set is compact, and so the same is true.
Do you require that phi s long phi t to be
Can you ask louder?
do you ask that phi s long phi t to be phi s plus t?
Yes, of course, it's a flow. So, yes. Hi. But okay, maybe I should have directly presented that with the geodesic flow, but to answer your question, if you move on a geodesic, you have a vector, you move it from t, and then you move it from s. Of course, at the end, you moved from t plus s. That's a flow. Okay, the notion that I presented, where is it? The topological notion of chaos can be translated in the vocabulary of ergodic theory. What is ergodic theory? Maybe I didn't say that. Ergodic theory is a branch of dynamical system where we study dynamical system with invariant measures. So it's just a part of dynamical systems. And so I come back to the title, chaos in ergodic theory. So I said, okay, one way to get chaos is to have many invariant measures. And as M1 is a convex set, if you have many invariant measures, you will also have many invariant ergodic measures. Another way is to say that the entropy, okay, there are measures with positive entropy. What is the entropy of a measure? Okay, it's more difficult to state it rigorously maybe, but it's the same intuition. But okay, you have your bad glasses with precision epsilon, and you will count how many distinct orbits of size t you can see, say, in a set of positive measures. Okay, so you take a set of measures, say a 1/2 at least, and you count how many orbits you can see. And okay, you have to be careful in producing an efficient definition, but it's the same intuition, but in the support of the measure. And so having measures with positive entropy is a way to get chaotic behavior. And you can hope that you have mixing measures. And then I come back to my first example in probability theory. What is mixing? No. So what is mixing? So a measure M is mixing if when you take two Borel sets A and B, the measure of A intersected with phi minus TB converges to M of A and M of B. What does it mean? It means that, okay, A and phi minus TB are not independent, but asymptotically it becomes independent. So it means that asymptotically, starting from A and arriving to B at time t, become more and more independent events. So it's a way to say your starting point and your future point become more and more independent. So that's mixing. And then, okay.
So here, the time going to minus infinity or plus infinity, you ask the same conditions, or do you?
Okay.
Or are they different?
No, look, it's mixing if for all Borel set A and B, you have say this with t going to plus infinity, but as the measure is invariant, you put okay, you understood? Okay. So I don't explain it, but so it's the same in the future and in the past. So that's mixing, and in the last maybe 2 decades, there were a huge industry of very hard work in dynamics to obtain, in certain situations, exponential mixing, which means exponential speed of convergence. And now, okay, there are people here that have a small workshop and that work in on such questions. That's a very hard analytical technology to get such results. And maybe it's a good place to say that almost everything that I will explain in my lectures is true in any dimension, in variable negative curvature, and even for many things on cat-1 spaces, for those of you who know what it is. And I just focus on hyperbolic surfaces because one asked me to focus on hyperbolic surfaces, but okay, most of the things I will say are true in general, but exponential mixing is, at the contrary, is something which is not very well known and true only in very particular situations, and for example, compact hyperbolic surfaces. But that's very hard dynamics. Okay. Now, so my goal is to, I will enter into the subject, but my goal will be to construct a family of measures, of invariant probability measures for the geodesic flow, a huge family, so it will show you that this set is large. These measures will be ergodic, have positive entropy, they will be mixing, and in some good situation, compact hyperbolic surfaces, Dolgopiat proved that they are exponentially mixing, but I will not enter this. And the point is that these measures are involved more and more in some problems of deformation of geometric structures. And so I will not speak a lot about it, but later on you could use them for your preferred deformation problem. Okay? So after a long presentation of what is chaotic behavior, until now, I'm focusing only on the geodesic flow of hyperbolic surfaces, okay? So, okay. No. It has been defined quickly in one of the short talks yesterday, I think, but I would like to recall what is the Busemann cocycle. That's a huge, an important tool. If I take 2 points x and y on the hyperbolic disk and a point on the boundary, and I look at the geodesic ray from x to psi and the geodesic ray from y to psi, I want to compare their distance to psi. And so the Busemann cocycle, when I do research alone in my office, I write it like that because it's comfortable for computation. But of course, it has no meaning because this is infinite and this is infinite. And the correct way to define it is to consider the limit and to prove that the limit exists of the distance between x and say, okay, I will call Cx of t the point on this geodesic, which is a distance t of x. And I consider the distance from x to Cx of t minus the distance from y to Cx of t. And convexity properties of the distance in non-positive curvature that allows you to prove that this quantity converges to something which is called the Busemann cocycle. And now the Hopf coordinate can be defined rigorously. So the Hopf coordinate is a homeomorphism from the unit tangent bundle of the disk to the circle times the circle minus the diagonal times r, and it associated to a vector v. So the two endpoints of the geodesic that it determines. The same picture that I drew a few minutes ago. And now I can tell you what is the real parameter. The real parameter is, okay, I have the origin of my disk, which is somewhere, I don't know. So this is the origin of the disk, and I will compare the distance of V and O to V plus. So it's a Busemann cocycle. Towards V plus between O and the base point of V. This is the base point of V. This is a map, and it turns out that it is a homeomorphism. And even if you want the regularity, it's a Hölder continuous homeomorphism. But if you don't know what does Hölder mean, or what is the topology on the right side, I don't want to focus on this, but it is a Hölder continuous still. The point is that these coordinates, as I said at the beginning, a product structure is very useful to get chaotic behavior. And so this coordinate will be very useful. And so it will be convenient to understand correctly these coordinates. They are still here. No. No, this is not so useful. That was big. It's a game. Non, il veut pas. Excusez-moi. I guess you will have the sheet of exercises. I put some properties on it that I don't want to prove, but that are elementary to prove on it. And for example, in these coordinates, if you have a vector v which has a coordinate v minus, v plus, and s of v, then it's very easy to understand the action of the geodesic flow and of the group gamma that is hidden from the beginning. So first, GTV acts by translation on the real coordinate. And that's extremely comfortable because translations are easy dynamical systems. And second, if you have a, so that's the occasion to recall that I consider a quotient of the hyperbolic disk by a discrete group, gamma. And so the T1S is also the quotient of the unit tangent bundle of the disk by gamma. And so gamma acts on the unit tangent bundle by, it's the differential of gamma that acts on the unit tangent bundle. And this action is very easy to understand in this coordinate. So this action of gamma on the hyperbolic disk can be continued on the boundary. And so it's a geometric action, which is, that you know, it's a projective action of gamma on the boundary. And on the real coordinate, it acts by addition of a cocycle. Once again, it's an addition, so it's very comfortable. And now I will look at the formula because I checked. Probably the formula on my notes are correct, so that's great. But you can check if it's correct or not and tell me if it's not. So you have, the main important thing is not the formula, is the fact that the formula exists. Okay, so the precise formula, okay, you retrieve it at the end when you have to prove something. Okay, and now I want to use these coordinates to understand invariant measures. Okay. You have questions so far? So, okay, I have my hyperbolic surface, which is a quotient of the hyperbolic disk by a group gamma. And so I have a natural projection, which is taking the quotient by gamma. But I also have a homeomorphism between the unit tangent bundle of the disk and S1 times S1 minus the diagonal. I will put a delta here to recall that I remove the diagonal times R. And the point is, okay, if I have an invariant measure here, I can lift it as the group gamma acts properly discontinuously on this space here. I can lift my measure. A measure is a tool to allow to measure every Borel set, but if you know how to measure every small Borel set, then you can measure every Borel set. So it's enough to be able to measure small Borel sets here, and so the projections allow you, okay, I let you in exercise, to convince you as an exercise that this is easy to lift this measure to a measure m tilde, and as it's a lift of a measure, if the measure here is invariant under the geodesic flow, then the lift will be invariant under the geodesic flow also. But it's a lift under a gamma action, so the lift will be invariant under gamma. Okay? And then, okay, I have this measure m tilde, which is invariant under the geodesic flow and invariant under gamma. And then if I look at it in this Hopf coordinate, so it means that I consider the image of m tilde by this Hopf homeomorphism. So let's say H is the Hopf homeomorphism. Then this measure, the image measure, it's a measure here, which is invariant under gamma and under the geodesic flow. But what is the action of the geodesic flow? It's an action by translation, okay? And maybe you learned once in your studies that up to normalization, the only translation invariant measure on R is the Lebesgue measure. There is only one, okay? So this measure is necessarily written as a measure on it times dt, okay? And a measure on it times dt, and I will call C the measure here. So this is a Lebesgue measure on A, okay? And this is a measure which is gamma invariant measure on S1 times S1 minus the diagonal. And this is called, this will be called a geodesic current. Geodesic current will be a gamma invariant measure on S1 times S1 minus the diagonal. And here I would like to, comment on dit, you should be careful about the detail, which is really not important, but it's important if you want to write precise things. Geodesic currents for geometers are often measures on S1 times S1 minus the diagonal quotiented by the, how do you say that, antipodal map. And for the people in dynamical system, it's important to precise in which direction you go. You don't want to say, okay, if you look at S1 times S1 minus the diagonal quotiented by antipodal map, it means that you look at a geodesic, whatever, without orientation. But in dynamical system, we need to know where we go. And so we need to keep track on the direction. But it's not very important, okay? But we work on this space. It's just a remark for those who know another definition of geodesic current. And so, okay. And this correspondence is a good correspondence for if you, okay, I should add a word to have something correct. If I consider a radon measure, radon measure is just a measure which is finite on compact set, and I lift it, I will have a radon measure on the universal cover, and then a measure like that, which is a radon measure also. If you don't know what it is, forget it. It's just a small remark for those who are interested in geometrically infinite surfaces. This gives you, this diagram gives you a 1-1 correspondence between radon invariant measure on the unit tension bundle of the surface and radon invariant measure and geodesic currents, but okay, it's just a small remark. If the unit tension bundle of the surface is not compact, you are not sure if you will get a finite measure or not. But for the framework of these lectures, if the unit tension bundle of S is compact, you can just forget what I said, okay? So if T1S is compact, this diagram allows you to think to these invariant measures in terms of geodesic currents, okay? So knowing, once again, it's very important, knowing M is exactly the same as knowing the geodesic current, okay?
I don't understand why H star of M had to have a structure of a product and not a C times a factor that would depend on the factor in dt.
That's an exercise. Okay, that's not a difficult exercise. Okay, maybe the hint is really, okay, this one, here is an addition, and here you have an addition. This is the key of the argument. Okay, that's an exercise. That's not completely obvious, but that is not difficult. Okay, I lost what I wanted to say. Okay, now, as I said, my goal is to construct a good family of measures that reflect the chaotic properties of the geodesic flow and that allow to study deformation. If I focus on the first point, I want to construct a family of good invariant measures that reflect chaotic behaviors. in view of what I said before, you should say, okay, I want to construct a product measure. That's the natural idea. And the most natural idea would be to say, okay, if I'm lazy, as I say often to my students, in math it's good to be lazy a little bit, but not too much, but a little bit. So if you want to be a little bit lazy, you say, okay, I would like to build a gamma invariant measure here, and then I do the product with the same one here and with Lebesgue here, and I get a measure of this form, which leads me to a Radon invariant measure. That's nice, lazy, good idea. But, okay, of course it does not work. Why? That's an exercise that maybe some of you did already. That's a very sad point. There is no invariant measure on the boundary, except if your group is completely trivial. So that's an exercise. That's really a very nice exercise that everybody should. There are more or less stupid exercises, but this one should have been done by everybody. So the exercise is the following. Oh no. Again?
If S is compact,
Yes.
can you get a correspondence with also non-finite measures?
No, because precisely, if S is compact, or in one direction you have a probability measure on T1S, you lift it, it will give you a Radon measure. That's okay. In the other direction, okay, there is a subtle point that if I have a Radon measure, I project it, I will have a Radon measure, and then you normalize. There is just this point of normalization that I don't want to develop. So what is the important exercise? So consider gamma, so a discrete group in PSL2R, which is non-trivial. Non-trivial means non-elementary, and non-elementary means you have at least two hyperbolic elements, distinct hyperbolic elements in gamma, which have distinct and attractive and negative endpoints. If you think to an interesting hyperbolic surface, its fundamental group will have at least two such elements. And so one says that they have a north-south, okay, one has an axis like that, and another one will have an axis like that. Then there exists no invariant probability, gamma invariant probability measure on S1. And well, that's sad, but that's life. That does not exist. Okay, if your group is elementary, for example, it's generated by just one isometry, you can consider the average of Dirac masses. So, but it's not very interesting. Okay, so we have to be more clever than that. And so the strategy will be to construct, so quasi-invariant measures on S1. And the naive idea will almost work. So you consider a quasi-invariant measure here. You do the product with itself. You have a quasi-invariant measure here. You add something to transform it in a gamma invariant geodesic current. and you do the product with dt, and you get invariant measure. And that's what I want to do now. Okay. So now I would like to present you a construction which is originally due to Patterson and Sullivan. So maybe some of you know it. Maybe less of you know it in the Gibbs version. So I will call it the Patterson-Sullivan Gibbs construction. It's not due to Gibbs, of course. So I learned this construction in papers of Patterson and Sullivan. If you want to learn it, the best place to learn it is the papers of Patterson and Sullivan for the historical construction, and the generalized construction. I learned it in a paper of Le Drapier, which is a nice paper, but I'm afraid that it's in French. Structure au bord des variétés à courbure négative, something like that. He says that it's due to Ammenstedt, but I never read the Ammenstedt source, and I would say that it's really Le Drapier's ideas. And in a work with Paulin and Policott, we wrote the construction in a non-compact setting, so it's also completely developed in the last book, but it's in a much more general setting. Okay, so first, consider a map F from the unit tangent bundle of the surface to R. And it will be, the minimal regularity is Hölder continuous. If you don't know what it is, you can think to C1 map, okay? If you know what it is, Hölder continuous is enough. But I must say that I'm not able to furnish an Hölder continuous map which is not C1, so okay, think to C1 map. The first thing is that I need a notation. If I take I will call F tilde as the gamma invariant lift from the unit tangent bundle of the disk to R. And now, if A and B are points in the disk, I need to introduce the notation. What will be the integral from A to B of F tilde? If I have 2 points on the disk, there is only one. There is a unique geodesic segment from A to B, parameterized with unit speed, and then let's say C of t, and this notation will mean, by definition, the integral from 0 to the distance between A and B of F tilde evaluated on the derivative C prime of t dt, where C is, once again, the geodesic segment from A to B. So it's the integral on the geodesic from A to B, but viewed on the unit tangent bundle. Okay, that's a notation. And now, we introduce the Poincaré series. Associated with the group gamma and the function f. No, why? No. It's a map. Continuous, Hölder continuous, C1. Okay. The Poincaré series, what does it what it is, it's the following series. It's a sum over all elements of gamma. Here comes the geometry of exponential minus s times the distance from O to gamma O plus the integral from O to gamma O of f tilde. If some of you know already the construction, probably a few of you, there are variants of this construction. It's not exactly the construction used in Le Drapier's papers. It's almost the same. And for example, some of you could know the work of Andrés Sammarino and collaborators, and they use the Le Drapier construction. And this way is almost the same, but it's more adapted to non-compact situation. That's really, if you don't understand what I'm speaking about, forget it. And maybe that's why you thought positive.
I thought you were going to do minus s times the integral.
Yes. And so, okay, we don't speak about it. It depends on your viewpoint. There are many viewpoints on this family of measure. I would like to emphasize that they have many, many rules.
Do you assume that the period is positive?
Not for the moment. Not now. No, not in general. Okay, there is one of my starting points on this story was the following. Okay, you know that there is a lot of invariant ergodic measures, okay? And what is a typical, you know that for those reasons, you know that the geodesic flow has positive topological entropy and is topologically mixing. You would like that typical invariant measure reflects these properties. So you would, as a dynamical people, you would like to find good invariant ergodic measures in the sense that they have positive entropy and they are mixing. But one can prove that is a very old result. I don't remember who did that, maybe Oxtoby or... In the compact case, it's very old and I extended it in the non-compact setting with if could-n. There is a generic measure in the bare sense. If you take a generic measure in this set, it will have zero entropy and it will not be mixing. So it's extremely frustrating. In a certain sense, a typical measure here is not chaotic. So the first point is that you want to produce many, many, many different measures. And so I would like, so I don't want to say my typical F is, because my typical F would say, okay, if you want a dynamic, a typical orbit that spends twice the time here than it spends here, you will take a potential which is maybe, okay, it will be larger here than here. If you want to avoid a certain zone of the dynamic, if you want to avoid, to do a hole here, if you want typical orbits that almost never go here, then you will take a potential which maybe is zero everywhere and minus 10 milliards here. If you want a measure which will reflect the whole geometry, maybe you will take F constant everywhere. So in this sense, I don't want to give you a typical. Typical is all the maps. So, and for different maps, you will have different behaviors. And that's, okay. That's my starting point of view. And then I realized that this family of measures have many, many other applications, in particular in deformation theory, but my first original point of view is this one. From a dynamical point of view, the main point is that you can do it for every F. Tic-tac, tic-tac. I would like to construct it before the end of the lecture, but the first lecture, but I consider this series, this is a series, and as an exercise, you can show that there is a critical exponent, which is defined as the lim sup of when t goes to infinity of 1 over t log of the sum over gamma such that the distance from O to gamma O is between t and t plus 1 of exponential. Okay, that's a number. Okay, this is a real number, and you can show that the series is converging if S is greater than the critical exponent, and is diverging if S is strictly smaller than the critical exponent. And then there is a apparently technical, but in fact deep point, but I will not focus on it today, which is what happens at the critical exponent. The Patterson introduced a great trick, which is explained in many bad ways in many papers. The best place to read the Patterson trick is Patterson's paper in ActaMath. It's very clear and it's very elementary and very tricky. So you can assume, up to modifying slightly the series, you can assume that the series is diverging at the critical exponent. Okay? And I will not develop, but that's some. Yes, a posteriori, if your surface is compact, or a posteriori, if you get a finite measure, it will be the case. But, that's why I don't want to focus. At the first day you see this construction, I guess it's not a good idea to. So now, I construct a probability measure on the disk. Maybe I didn't say. If you never saw this, and if you are, okay, you are, most of you are very young, but if you are young at the beginning of a PhD or in the middle of a postdoc, it's not the same. And so if you are very new in the subject, you can just take f equals 0, and then you get a classical Patterson-Sullivan construction, and then it's already a very nice construction. You will just get one measure, but it's a very important one. Okay, now I define a probability measure, which is 1 over this series times the sum it's a sum of Dirac masses. So I'm on a hyperbolic disk, and I have the orbit of gamma. And I consider a probability measure, which is a sum of Dirac masses at all points of the orbit, okay? And with a certain weight. This is a positive weight, and it's normalized, okay? This is for S strictly larger than the critical exponent. And then so it is a probability measure. It is done as a probability measure on the disk. But the disk is included in its compactification. And the compactification is compact, that's nice. And so as the compactification is compact, you can consider a decreasing sequence Sn going to delta f. There exists such a sequence such that nu f Sn converges to something, to a measure, a probability measure. A priori, it's a probability measure on d bar, okay? What is convergence of measure? Convergence of measure is convergence of all the integrals of all continuous functions. Okay, I will go a little bit faster to go to the construction. Okay. As an exercise, you can prove that as I assumed that the series is diverging at the critical exponent, this implies that the limit measure is supported on the boundary. Okay? And even more, if you think of it, we saw yesterday the definition of the limit set, which is a set of limit points of the orbit in the boundary. So the limit set is a set of accumulation points of any orbit in the boundary. And in fact, you can show that the measure is supported on the limit set inside the boundary. Okay? And now I have a measure. I will let you as exercises properties. That's very elementary exercises. But if you don't succeed, you can ask me later, if I remember how to do that. That this measure is quasi-invariant. And the precise relation is the following. And the formula is probably correct, up to signs maybe, but I checked. You have a quasi-invariance relation that can be checked in an elementary way. What do you see here? That's the critical exponent delta f. That is the Busemann cocycle that I introduced earlier. And that I didn't define it, what it is. This is a cocycle associated with f. You have the point gamma O somewhere. You have the point O. Then you have a cocycle consisting to integrate f from gamma O to psi and from O to psi. And so rho c f from gamma. It is essentially the integral from gamma O to psi of f tilde minus the integral from O to xi of f tilde. But of course, you have to define it rigorously in a with a limit procedure. And then you have a measure on S1 times S1 minus the diagonal. You have a measure which is something times nu f of psi, nu f of eta, and the formula is here. Okay, okay, maybe you will see the notes. It's a formula which is done so that this is gamma invariant. And this is an explicit formula in terms of these cocycles. You can really see the notes on my webpage. It's completely explicit, but it does not help you to understand anything. And so it allows you to construct a measure m tilde f, which is the image of this one times dt through the inverse of Hopf coordinates. And you get a measure mf on T1s. And okay, this is a measure. For every f, you get a measure. And okay, if the surface is compact, then, or convex co-compact, it's the same, then this measure is finite, and then you can normalize it as a probability measure. And as a teaser for my second talk, I would like to say that these measures so at least if T1S is compact or convex to compact, these measures MF are ergodic. They are mixing. They have positive entropy. They maximize a quantity which is called pressure. What else? You can show equidistribution, weighted equidistribution properties of periodic orbit for those who know what it is. And these measures appear in many deformation problems. And I guess I will stop here.